Hello, Chem 213 students, and welcome back to our third lecture for this week here, where it'll be our fifth and final lecture on Chem 212 review. So when we finished last time, we had covered uh, substitution and elimination reactions and addition reactions in part 3 of this series. Then in part 4, we discussed alkyne reactions, radical reactions, and strategies and approaches to synthesis. Now, synthesis is something that takes a lot of practice. I only showed you one example here. Really, this just involves doing many of these problems. So Chapter 11 is just a great problem to look at when you're trying to review and make sure you have a kind of comprehensive view of all of the previous chapters in the textbook. And then synthesis continues to happen as we have our new reactions, and we'll have even more and more complex synthesis problems as we move forward. Some of these reactions that will be very important are those regarding alcohols. Before we discuss the reactions of alcohols, we should also think about the physical properties of various molecules. So we've been learning about reactions of molecules with various functional groups, and now we finally get to the alcohol functional group, which is the first of our functional groups presented in the textbook that contains a very negative bond between an OH or an NH. And these tend to produce hydrogen bonding intermolecular forces. And you can see that when hydrogen bonding, so we have hydrogen bonding forces present here for the alcohol, these tend to much stronger intermolecular forces that will then cause the molecule to have a much higher boiling point because the molecules are much stickier to one another. So alcohols can be involved in hydrogen bonding. With alkyl halides here, you do have this one polar bond. So these have dipole-dipole forces due to having at least one polar bond and being asymmetrical in this way. The electrons are pulled towards the chlorine. And then you can see that all molecules here have London dispersion forces. But the nonpolar molecules, that's the only force they have. And these tend to be small unless the molecule is very big. So alcohols tend to have high boiling points due to their hydrogen bonding. In terms of solubility, when we think of solubility, molecules will dissolve in one another or mix well when they have similar overall polarity. And with alcohols, you can see that depending on the size of the hydrocarbon chain with the alcohols, you can have a molecule that is, quite polar, like methanol, very polar, due to the fact that the polar region takes up most of the entire molecule here, with there just being one carbon. But as you have greater and greater hydrocarbon chain, which does not have polarity to it, you get a less and less polar molecule. So the hydrophilic or water-loving region becomes a smaller part of the entire molecule. So the whole molecule gets less and less polar, and thus would be less and less soluble in polar substances such as water. And so, yeah, whoops, I repeated those slides. Okay. One other thing to consider now that we're going to move on to discussing the reactions of alcohols rather than their physical properties is that important reactions in alcohols are those that involve the oxidation of the alcohol to produce carbonyls. So we can see here are the calculated oxidation numbers for carbon in the middle of each of these molecules. I'm not going to go into the detail of these. What I rather look at is the differences. So as I discussed previously, when we have more oxygen atoms or more bonds to oxygen atoms, we can call that oxidation. More oxygen atoms. So as we go from an alkane here to an alcohol, relative to one another, the methanol is oxidized because it has a greater number of oxygen atoms. And we can see it as a result, the carbon here has a higher oxidation number. And then moving from left to right here, we're going to have more and more oxidation. So when we go to the oxidation of the alcohol, we get an aldehyde, carbonyl here, formaldehyde, that has a carbon with two bonds to oxygen. So we have more oxygens or more bonds to oxygen. Here we have another oxygen atom added, further oxidizing the molecule. So this aldehyde here can be oxidized to a carboxylic acid. Finally, if we have a carbon with 4 bonds to oxygen and 2 double bonds, we have its most oxidized form. Oxidation can also occur when we have less hydrogen atoms, right? And the opposite is true for reduction. Less hydrogen can also be oxidation. And the opposite is true. Reduction is fewer oxygen atoms or more hydrogen. And that's a simple way of looking at oxidation and reduction. When it comes to oxidizing an alcohol, there are many there are many oxidizing agents that we can use. We'll discuss some of them later, but generally they involve chromic acid or sodium dichromate. If you have a carbonyl, you can reduce it to an alcohol. So remember that adding hydrogen is reduction, as we mentioned there. So you can see we lose a bond to oxygen and we add a hydrogen. So that's reduction. And this can be done with a variety of reducing agents, one being sodium borohydride, but practically speaking, lithium aluminum hydride is a little bit easier to use. Remember that when we do reduce the aldehyde to an alcohol, we often produce a chiral center. And so this chiral center here, the ultimate product, if the carbon here is chiral, is that you will get a racemic mixture of both of the stereoisomers, which is something that's important to remember. So in the alkyne chapter, we also learned a reaction where we deprotonated the alkyne and used it as a nucleophile in order to make a molecule with a longer hydrocarbon chain. And that was the only way we had to do that, using that deprotonated alkyne carbanion. Well, it turns out there is another way to do a reaction in which we have a carbanion, and that is involving a so-called Grignard reagent. So the Grignard reagent is the reaction of an alkyl halide with magnesium metal, and this produces a bond in a reaction for which the mechanism is not completely known. The magnesium makes its way between the carbon and the bromine here, and you end up with this reagent, which really behaves as would a ionic compound. And so essentially we have the carbanion here, and then the MgBr is positive informal charge. And now this carbanion can behave as a nucleophile. And that's shown right here. So it's drawn again. The carbon is much more electronegative than the magnesium, so essentially it's keeping most of the electron density here. And so we have this carbanion here, and then we have this cation with the magnesium bromide. And so it will behave like a carbanion. So then once you've reacted the magnesium with the alkyl halide, you get this carbanion result. This carbanion can behave like a nucleophile, and it will attack. And remember, you shouldn't memorize this. You should think about, why will it attack here at this position? Well, it's because this oxygen is very electronegative compared to the carbon. So the carbon right here is partially positive on this side. So maybe I should draw it a little closer to the carbon. Partially positive here. So the negative nucleophile wants to attack there at the bottom of the carbonyl, the carbon attached to the oxygen. Simultaneously, we can't have a carbon with 4 bonds, so the electrons here are now residing in the unhybridized p orbital on the oxygen, and then this can go on and do a deprotonation. Ultimately, we get the alcohol and a fully sp3 hybridized oxygen at the end after this reaction. And so the ultimate result is that we have lost the carbonyl, it has turned into an alcohol, but we also have additional carbon atoms from this R group attached to that same carbon. And this is a Grignard reaction. This is our second way of having a new carbon-carbon bond. Very important for synthesis. Now, if you have an alcohol, however, on the same um, on the same reagent that you want to make into the Grignard reagent, you first have to deprotonate the alcohol, or protect the alcohol rather. The reason being is because, remember, if you use the Grignard reagent here, you're going to get a carbanion. And that carbanion will be extremely basic. So any carbanion, any R group that's produced by the Grignard, like let's say over here, this can be produced on the same molecule. It will go and it will deprotonate this alcohol, and then at that point, this we'll have this deprotonated alcohol, and we won't have the product that we were trying to get. And so it's important before we do this, and we're just going to get a longer chain, right? We're going to get an ether instead. We don't want the ether. Rather, or at least a deprotonated alcohol, which could ultimately lead to an ether. Anyway, if you're making a Grignard with a molecule that has an alcohol, to avoid the reactivity of that alcohol, we should first protect it with trimethylsilyl, the trimethylsilyl group, and that's abbreviated as TMS. So you use TMS chloride and triethylamine, and this will install the trimethylsilyl group to protect the oxygen. Then we can go ahead with our Grignard reaction. So we'd create a Grignard on this, we'd react with the carbonyl, and now we would get this carbonyl here turning into an alcohol, and we have now the whole group that we meant to nucleophilic attack here. So this turns into the carbanion here, and a nucleophilic attacks right in here. Then at that point you can use so-called TBAF to deprotect, and then you'll get your alcohol back. You'll replace the TMS with the alcohol. And so be careful when you're using a Grignard reaction. If you want to use a reaction that or a reagent that already has an alcohol as the Grignard reagent, you have to protect the alcohol first with TMS. In addition, we saw in chapter 7 that alcohols are terrible leaving groups. And so if you want to do a substitution reaction involving an alcohol, well, first you have to do one of two things. You have to either do it in very acidic conditions, so the alcohol can be protonated, and then the leaving group would be water and not hydroxide, which is much more stable. Or you can react the alcohol with tosyl chloride and impurity solvent. And the tosylate here is a big group containing a sulfate and a benzene ring. We've seen this before, but you can simply abbreviate it as TS. At that point, if you have a nucleophile, this nucleophile can now attack in an SN2 style, and then you'll get this product. Note that this is an SN2 type reaction, so the stereochemistry is inverted here. So the halogen is on the dash, even though the tosylate was on the wedge. One thing to note is this replacement of the hydroxyl with the tosylate does not change the stereochemistry. But the SN2 reaction of the subsequent nucleophile does. So here, if we want to do, for example, an elimination too, it's the same thing. Both substitutions and eliminations require the hydroxyl to be a good leaving group. So we would start by replacing the alcohol with a tosylate, and then we would follow that up with a base to produce the E2 reaction here, in this case. So note that E2 is not susceptible to rearrangements the same way E1 reaction is as well, if an E2 reaction occurs. So in summary here, for our alcohol reactions, the important alcohol reactions we have learned have been the oxidation and reduction to produce alcohols, reduction of carbonyls to produce alcohols, oxidation of alcohols to produce carbonyls, and also our Grignard reaction as well, which isn't on this slide. But this bottom part here is a great summary of the oxidation and reduction reactions for alcohols. So if you want to oxidize an alcohol, as I said, you'll use chromic acid PCC is another alternative. These are some others here. I'll always refer to these ones here. If you want to reduce ketones and aldehydes, the best choice is lithium aluminum hydride followed by water, but sodium borate hydride followed by methanol will also work. In addition, some reactions that are discussed in chapter 12 regarding the replacement of an alcohol with a chlorine or a bromine atom. These ones, the mechanisms are not well known. They're not completely known. However, if you react with a hydrohalide, you'll get a substitution reaction. First, the hydrohalide is there to protonate the alcohol, so it leaves as a water. Alternatively, you can use SOCl2 and pyridine to replace the OH group with a chlorine atom, or PBr3 to replace the hydroxyl group with a bromine atom. These tend to be very synthetically useful reactions, particularly if you want to go and do a elimination after and produce an alkene. To go backwards and turn the halide into an alcohol, you would do a SN2 reaction with a hydroxyl group or SN1 reaction with water. Finally, the formation of an alcohol from alkene. We have several ways to do this that we've discussed before. We can do acid catalyzed hydration, hydroboration oxidation. Remember, this will produce the less substituted alcohol. This one will produce the more substituted alcohol. And if we want to produce the more substituted alcohol but avoid any carbocation rearrangements, we use oxymercuration, demercuration, with mercuric acetate, NaBH4, and NaOH. Finally, if we want to eliminate the alcohol and produce an alkene, we can do this as a acid catalyzed elimination with sulfuric acid, or we can use tosyl chloride and pyridine to replace the alcohol with a different group and then follow that up with an elimination. So that's a summary of the alcohol reactions and how they relate to a lot of the other reactions we've learned previously. Next, the other part of chapter of the chapter here, or next in the next chapter rather, in chapter 13, the focus is on ethers and epoxides. And so in ethers, we've seen previously, just like the alcohol chapter, a lot of what was in there we had seen previously as a part of our addition reactions chapter or our substitution reactions chapters. Chapters 7 and 8 are extremely foundational to all of this stuff. Now, if we have if we want to prepare an ether here, we're going to see a couple of ways to do that. So remember, an ether is a functional group that has, rather than a oxygen bonded to a carbon, rather than carbon, oxygen, hydrogen, which is an alcohol, an ether is carbon to oxygen to carbon. And so that's an ether. And so what we can do to produce an ether, one way to do it is with so-called solvolysis. So if we have ethanol and we put it in an acidic environment and we have ethanol as the solvent and the reactant, in the acidic environment we can protonate some of these alcohols, which we've written as a two-way arrow here because these are definitely very close in terms of pKa's. So this reaction can, or these two rather, these two are very close in terms of pKa's, these two acids. So this reaction can easily go backwards as well. But once it's gone forward, since you have lots and lots of ethanol, there is this likelihood of a bumping of one ethanol molecule into this protonated ethanol to do an SN2 attack on the backside here of the carbon attached to the oxygen. And then water can leave as a stable leaving group instead of hydroxyl, which would not. So the protonation had to happen first to make a good leaving group so the water can leave. But at that point, we've had the nucleophilic attack by a neutral nucleophile. So this oxygen was making 2 bonds and had 2 lone pairs, but now it's making 3 bonds and has 1 lone pair, so it's positive and formal charge. So the final step is to deprotonate that protonated ether, and we've got lots of this ethanol around, so this can easily grab the proton off the ether and ultimately produce the stable ether. So we can do this to produce simple symmetrical ethers. Symmetrical because both the reagent and the substrate here are ethanol. So either side of the oxygen is going to be, the other side of ethanol, basically. We're going to have two carbons on either side. If you do propanol, it would be the same thing. And so this is only going to be useful for symmetrical ethers. What if we want to make asymmetrical ethers? Then we would want to use the so-called Williamson ether synthesis. So this involves the deprotonation of the alcohol of interest with an extremely strong base, or quite a strong base. Sodium hydride, we'll use the hydride ion. That will do a deprotonation, leaving the lone pair here on the oxygen. And then finally, we'll introduce an alkyl halide so that we can initiate an SN2 reaction. And with this primary alkyl halide, or with this alkoxide ion and this primary alkyl halide, we'll get primarily this SN2 product. We will have some competition with E2 as well. If we had a larger alkyl halide. In this case, there would be no E2 because we would need a second carbon atom to do an elimination. So this tends to work best with like methyl alkyl halides or unhindered primary alkyl halides. That way that the SN2 reaction will dominate. If it's secondary or tertiary, you're going to get mostly E2 reaction instead. So the opposite of creating the ether would be to break apart the ether and get the two sides of the molecule separate and get an alcohol and some other alkyl halide, for example. So if we have this ether and we expose it to a hydrogen halide here, we're going to get a deprotonation of the hydrogen halide here. It's going to give its hydrogen, and then we'll have the protonated ether. This oxygen is making 3 bonds with one lone pair. This can then, we still have the halide ion, which can then do a nucleophilic attack on the carbon attached to the oxygen, because remember, oxygen's pulling electrons its way, so it's going to be partially negative by the oxygen, partially positive here by this carbon. And then ultimately we get the alcohol here remaining that's left. So this alcohol on this side is this right here. And we get the alkyl halide also. And if we have an excess of HX, we can actually do this a second time and produce a second alkyl halide. What would remain here? So we'd protonate the alcohol. We'd have the halide that can behave as a nucleophile that attack the carbon, and we'd have a loss of water as a leaving group. And so this is the cleavage of an ether to separate that ether into an alkyl and an alkyl halide. And then if we do it again with an excess of HX, we'll actually produce 2 units of the alkyl halide and water. An important thing to note is that ethers will undergo auto-oxidation, which is a free radical mechanism. So we discussed free radical mechanisms in chapter 10. But for this one also relates to ethers, because these ethers, if you leave them on the shelf with exposure to oxygen, they're going to undergo auto-oxidation. So what this means is that you're going to get on the carbon next to the oxygen, you get a peroxide here, a hydroperoxide, the hydro meaning hydrogen, and then peroxide here. This hydroperoxide is highly reactive, and if you jostle the bottles too much, it can be explosive. So that's something to be careful about when ethers are stored for long periods of time. This starts with a radical initiator. So radical initiator could be oxygen itself, or it could be something else such as a halogen molecule or peroxide. But usually it's going to be oxygen. So let's say you have oxygen, and oxygen is shown right here. Oxygen behaves like a diradical, especially in the presence of other radicals. And so this oxygen could itself be the initiator or another initiator. You'll get one electron coming from the radical initiator, one from the bond between the hydrogen and the carbon neighboring the oxygen, and one electron then is left right on the carbon neighboring the oxygen. So if there's oxygen available, close to this ether, then we can have a coupling between the oxygen diradical and this carbon. And remember, oxygen behaves as a diradical because its double bond is essentially being pulled apart by the strong electronegativity of each oxygen atom. And so that's why it makes sense sometimes to write these as O2 as a diradical to indicate how it can behave in a radical mechanism, as a part of radical mechanisms such as this one. So finally, this leaves now, when this coupling occurs between these two, this still leaves the radical right here. And so we still have a radical. So this radical can go and undergo a hydrogen abstraction on a neighboring ether, and then we'll get a bond between this oxygen and this hydrogen. But now we've created another radical here. And so this will continue and continue, and this will produce a large amount of these hydroperoxides, which will ultimately be quite reactive and potentially explosive. When it comes to ethers that are in a ring here, like this one especially, these are called epoxides, ethers in a ring, particularly those in this three-membered ring here. And these epoxides, this one here, these have a significant amount of ring strain because this angle is forced into close to a 60-degree angle, whereas this carbon is sp3 hybridized and should be a 109.5 degree angle. So you have a huge amount of ring strain, which makes these actually quite nice electrophiles, because the nucleophiles, and we have a bunch of nucleophiles listed here, including alkoxide ions, which we have to be careful because they can also behave as bases and do elimination reactions. But if we have this guy attack the epoxide, it will open up, and then this OR group will be attached to the carbon on the epoxide, and ultimately the oxygen here will get protonated, and we'll get an alcohol, 2 carbons, 1, 2, 1, 2, away from the OR group. We can use cyanide here, another great nucleophile, hydrosulfide, great nucleophile. Another nucleophile would be the Grignard reagent, where we have a carbanion, and then we have the MgBr+, but that's not involved in the reaction. And then also, hydrogen can be added by the use of a soft reducing agent, such as lithium aluminum hydride. One important to note is that these ring openings of these epoxides are both regioselective and stereoselective. And just as a side note, recall that the way we get epoxides is by, if we take an alkene, we can react with a peroxy acid and get the epoxide. So when you have an epoxide that is not protonated, we're going to talk about protonated in a second, but when you have an epoxide that's not protonated, this reaction is going to be driven by kinetics, and the less substituted carbon here is going to be more open to nucleophilic attack. So the nucleophile will want to attack whichever carbon here is least sterically hindered, and then the epoxide will open up. However, the epoxide can be made even more reactive by the protonation of the oxygen, which will make the leaving group, in a sense, of the epoxide be this OH group with a carbon attached, which is a much more stable leaving group, because when it leaves, it will leave without a formal charge. So upon exposure of the epoxide to an acidic environment, we can get a proton transfer like this one here from the hydronium. Then we can have a nucleophilic attack by any nucleophile. It doesn't have to be water, but it can be. And this is in an SN2 style, so it attacks from the back. Then we get the loss of the leaving group. And notice, when this leaving group leaves, now it leaves as a neutral OH group. And so this means that we can use, in this kind of reaction, if we have an acidic environment, we can even use weak nucleophiles like water and still get an SN2 reaction. This is different from what we may have seen in Chapter 7, right? Weak nucleophiles, weak bases like water, tend to only support SN1 or E1 reactions and only in tertiary substrates. But if we protonate these epoxides, they're the ring wants to break so much that even weak nucleophiles are sufficient to initiate this reaction. Finally, though, when the water attacks, we had a neutral nucleophile attacking, so this carbon ends up with 3 bonds, 1 pair, positive formal charge, so it needs to be deprotonated by neighboring water to complete the reaction. And so we have a proton transfer, this pair of electrons takes a bond with this hydrogen, and another pair of electrons is left behind the oxygen, giving it 2 lone pairs and 1 bond. And so now it's neutral. So one thing to note, though, is under acidic conditions, this process becomes a bit more thermodynamically driven than in the situation where the epoxide is not protonated. So, for example, if you react with a hydrohalide, the first step here is going to be the protonation of this epoxide, HX. So we're going to have the proton transfer here, and that's going to give us now the protonated epoxide. Whoops, and I forgot the hydrogen. Should be drawn straight up, but I put my electrons in the way. But we have this protonated epoxide now, and now when the nucleophile attacks, it's not just going to be the kinetics that decides where it attacks. It's going to be the thermodynamics as well. So if we have a primary site, the nucleophile will attack at the primary site because the kinetics will drive that reaction. And it will be so less sterically hindered that it will be much easier for it to attack here. However, if a tertiary carbon is present, the nucleophile is going to attack at the more substituted position. And this is because when we have this is only for the protonated version. When we have the protonated version, now we have the situation where in this ring opening, so when this ring is opening, we've got the positive formal charge here. And now it's going to become partially positive here, and it's going to be partially positive here. So this is very analogous to what we saw when we were looking in chapter 7 and looking at these, or rather chapter 8, the addition reactions, and we talked about epoxides. The fact that now this is a positive formal charge, we have a positive formal charge on this carbon kind of partially as this bond is breaking. And that positive formal charge is much better stabilized on the tertiary position. And so the nucleophile will, in the protonated epoxide, end up attacking at the tertiary position instead of the primary one. Finally, thiols. We didn't say much about thiols, and we don't say much about them except to say that when we oxidize a thiols by removing hydrogen, remember removing hydrogen is oxidation, instead of getting a carbonyl like we would for an alcohol, we get a so-called disulfide linkage. And this is going to be really important when we study proteins later. It's an important bond between two cysteine amino acids in proteins. Produce a so-called disulfide bridge in proteins. And this can be achieved with the use of sodium hydroxide and water in the presence of bromine here. So the way that this works is, and sorry, this is supposed to be, I don't know what happened to my slide here, but this is supposed to be a negative, this is supposed to be a positive. And so here we have this, if we have a sulfide here, sodium sulfide of some kind, it can attack the bromine here, and then we get a bond with the bromine, we have sodium bromide. Finally, another deprotonated sulfide can attack, and these have been deprotonated by the sodium hydroxide. And then when it does, you get an SN2-like reaction where the sulfur bonds with the other sulfur, and you get the disulfide linkage. Oops. And that's the main thing that you should know about thiols and their reactions, that their oxidation results in a disulfide linkage, and that this is the mechanism here. Finally, our most important topic, and the one that we began to discuss in lab during this early period, is a review of spectroscopy, in particular infrared spectroscopy, which is one of our best tools for identifying the products of our synthetic reactions. Although IR spectroscopy is limited, IR spectroscopy only tells us the functional groups in the compound. In the next chapter after this, as we start Chem 213, we're going to learn about the powerful technique called nuclear magnetic resonance spectroscopy, which uses radio waves to align the spins of protons in the nucleus. And this allows us to determine what neighboring nuclei there are on neighboring carbons in the structure of the molecule. So this gives us indications of which carbon atom is bonded to which other carbon atom and which hydrogen atoms those are bonded to. So when we start next week, we're going to be focusing a lot on nuclear magnetic resonance spectroscopy. But first we need to have a good grasp on IR spectroscopy, because these two techniques are usually used in tandem to help you determine the overall structure of the molecule. Also, another important type of spectroscopy that you've probably used simply for determining the concentrations of substances is UV-vis spectroscopy. As we're going to see later on when we talk about molecules with conjugated pi bonds, meaning extended pi bond systems with extended parts of delocalized electrons throughout the molecule, is that these are going to absorb visible and ultraviolet light. And so we'll get to get information about the structures of these molecules from that type of spectroscopy as well. So let's start by talking about IR spectroscopy. Now, there's a lot that you can memorize about IR spectroscopy, but what you should really know, straight up memorizing this, isn't nearly as useful as understanding why IR spectra have the structure that they do. First of all, the position on an IR spectrum is going to be determined by the frequency, which is expressed in a unit called wave numbers, which is it's the inverse of the centimeter. So it's 1 over centimeters for the frequency of the vibration of the bonds. And the stretching vibration of a bond depends on the strength of the bond and the mass difference of the atoms that are bonded together. So a stronger bond will have a higher stretching frequency. And that makes sense, right? Think of a stronger bond like a stronger spring. It will vibrate more quickly. If you have a very strong spring, you pull it, it will go and vibrate real fast. However, if you have a very weak slinky and you let that down, let's say you let that go and go up and down, it's going to vibrate at a much lower frequency. So a stronger bond indicates a higher frequency of vibration, meaning the vibration energy levels are going to have a larger energy gap, because energy is directly proportional to frequency with a proportionality constant called Planck's constant, which is really just a very small number. With a CO bond here, the CO bond is much longer than the CH bond. In fact, most bonds to hydrogen tend to be very, very short because hydrogen is so small. And so because it has the longer bond, it's a longer and weaker bond. Most longer bonds are weaker usually. And so it's going to vibrate at a smaller frequency. So its vibrational energy levels are going to have a smaller energy difference. And IR spectroscopy works by the fact that IR light is absorbed at these very specific frequencies that are going to indicate certain vibrations indicating the presence of bonds between certain specific atoms. So here's what a plot looks like. It's plotted in terms of percent transmittance, meaning how much light got through. So the very top here means almost nothing was absorbed, and as the peaks go down, you have more and more absorption. The wave numbers here is the frequency in centimeters divided by the speed of light in centimeters. And we call these absorption bands. The values range from about 400 wave numbers to about 413. And we have particular parts of these shapes that we're interested in. For example, what is their wave number position? What frequency? Is it over at 3500 or is it over here, at 1500? The intensity. Notice that some of these peaks are not very intense. They don't have a lot of absorption. Others are very intense. And finally, shape. Are they broad or are they narrow? Are they So this is a very broad OH stretch, and then we can see much more narrow peaks over here. What does the shape of the peak look like? First of all, the relative position by wave numbers depends on the strength of the bond. Short bonds to hydrogen tend to vibrate to be the strongest and to vibrate at the highest frequencies. Triple bonds are stronger than double bonds generally, so they vibrate at a higher frequency, somewhere between 2100 and 2300. Double bonds here also stronger here than single bonds, so they vibrate at a higher frequency than single bonds, about 1600 to 1850. And then finally, single bonds tend to be below 1600 in terms of wave numbers. And there tend to be a lot of these single bonds on a spectrum, and they produce a lot of peaks, along with other bending frequencies as well as stretching frequencies. So it can be very difficult to pick out single bonds. It's the functional groups that we're mainly looking to find, or rather than carbon to other atom single bonds. Single bonds to hydrogen, of course, are way up here. Any bond to hydrogen is going to be very short, very strong, very high frequency vibration. So you can see that difference here when we look at the intensity here. Note that so that's the position of the peaks. Now, let's discuss the intensity of the peaks. So notice that if we have a carbonyl here, which carbonyls usually pop up around 1700-ish, carbon-carbon double bonds, a little bit lower frequency. Why is that? Well, it's because the carbon-carbon bond is, well, we can see it here. It's a little bit weaker than this carbon-oxygen bond. Stronger signals are observed when there's multiple of the same types of bonds. So if you've got two alkenes, for example, right at the same frequency stretching, you might get a bigger peak here, or a little bit wider peak as well, because you have two different signals very close to the same frequency. CH bond. So in terms of the intensity depends on the polarity of the bond as well. Carbon-oxygen, very polar bond, you end up with a more intense signal than carbon-carbon bond, which is not polar. Although carbon-hydrogen bonds are not very polar, they can give strong signals because there's so many of them. So the intensity is related to the polarity of the bonds, more polar being more intense, and also how many there are. So when you see sp3ch bonds, like going back to this spectrum here, these tend to be very intense because there are so many of them right on top of each other. One thing to note is that if you have a completely symmetrical molecule around a double bond, that symmetry will mean that you're not going to get any signal from that bond, because the signal comes from the absorption that is due to that is produced when the molecule vibrates, right, and the light is absorbed, and that energy that leads to an increase in the vibrational energy level of the molecule. But if it's completely symmetrical like this, there's no, well, just looking at the intensity here, this is taking it to the opposite extreme. We have greater difference in electronegativity between these atoms, so we get the most intense signal. If we have exactly zero difference between either side of this double bond, the signal is going to become nothing. It's that difference here that produces that magnetic field that allows for the absorption of this. So a completely symmetrical molecule around a double bond won't give you that double bond signal at all. That's something to keep in mind. When it comes to OH groups, again, bonds to hydrogen are going to be way up in the high frequency range because they are very short and very strong bonds. However, OH bonds are often participating in hydrogen bonding, which basically results in a pulling on that oxygen-hydrogen bond. And so for each of these molecules that are with the oxygen-hydrogen bond are going to be in a slightly different environment depending on how close they are to another oxygen-hydrogen bond where they are participating in hydrogen bonding. And so that leads to a varying degree of different stretching frequencies and a wide peak here. If you have a free OH not involved in hydrogen bonding, for example, it's very dilute in a solution of something else, this will give you a more narrow peak because all the bonds will be much more similar to each other, a similar environment. Whereas each of these OH bonds, due to their differing distance from the neighboring molecule, are in different hydrogen bonding environments and have different strengths of their OH bonds, and thus different vibrational frequencies. With carboxylic acids, with a carboxylic acid here, you have a carbonyl and you have an alcohol, both attached to the same carbon. And so what you have here is extreme resonance if this is deprotonated. So carboxylic acids can be easily deprotonated because they're quite acidic for an organic acid. And so what you can have here is if you have this deprotonated carboxylic acid, you have a significant amount of resonance here. So the resonance arrows, I can draw them. And when you have resonance, this means basically that this bond is not completely a double bond. It's somewhat a single bond. And this is not completely a single bond. It's somewhat a double bond. And it's like each of these bonds are weaker than they might otherwise be. And so you get this very downshifted due to the weaker bond, OH here, and you can see that it runs all the way down underneath 3000 for a carboxylic acid. You also get this carbonyl peak, and this carbonyl peak tends to be on the lower shifted side too, around 1700 for similar reasons. So this is the kind of visual you should have in your mind when you see something like this, the OH just spilling into the 3000 region. You should be thinking this is coming from a carboxylic acid, especially if you see the associated carbonyl. When it comes to amines, amines have two separate different types of environments, whether they're a primary amine, which has 2 hydrogen atoms and 1 carbon atom attached, or a secondary amine, which has 2 carbon atoms and 1 hydrogen atom attached. In the primary amine, you've got 2 stretching modes that are possible. The ones where the nitrogens stretch in phase, and the other one where they stretch out of phase. And that gives you 2 separate stretching frequencies, both kind of broad due to the hydrogen bonding, because NH bonds do have hydrogen bonding. If you have a primary amine, though, you don't have that. You only have one single broad signal, again, due to the hydrogen bonding in the NH. One thing that I want to mention as well that I didn't mention as much specifically, but is on the review that I gave you, is to remember that also you should always be looking here at the 3000 line. For below 3000, you have sp3ch bonds here, which are carbons that are bonded to 3 other carbon atoms. If you have a carbon double bond to carbon and you have a hydrogen, that's going to give you peaks just above 3000. And if you have carbon-carbon triple bond, it will be something like here. In addition, at around 2850, if you have a carbonyl and you have an aldehyde, essentially, that you get a carbon hydrogen bond here too, and that you'll end up seeing around 2850. The best way again to do these is to practice. You've done a lot of in lab. There's a nice practice with 8 different molecules. I encourage you to look carefully at those spectra, and you can look up. If you search the spectra on Google, you can find the ones from NIST. So you can search, for example, let's say you want to search a carboxylic acid. You search benzoic acid IR spectrum, and you can see the actual spectrum and try to break down what you see on that spectrum relative to what you've learned about where these peaks should be and what their shapes should be. Another powerful technique for characterizing the products of our reactions and various molecules is mass spectrometry. So whereas IR will tell you about the types of functional groups in the molecule, mass spectrometry will tell you about the mass, the overall mass of the molecule, which we call, in the context of spectrometry, we're going to call it the molecular ion when it's being detected by mass spectrometry. So the mass of the whole molecule, and also the way that the molecule breaks apart when it is ionized, can tell us something about the structure of it. Not as well as NMR, but in many cases it can be a nice supplement. So in the mass spectrometer, the compound is vaporized. It will be ionized usually by what's known as electron impact ionization or a high energy laser. then it will fragment due to that excess energy added to it, which causes the molecule to vibrate, sometimes so much that the bonds break. And then the masses of the ions in the fragments are determined. So the most common method of ionizing molecules is by electron impact. You get high energy electrons or light and shoot it at 16. This energy being about 1600 kcals per mole, and you break these. Electron impact will usually cause an electron to be ejected from the molecule. So essentially, we shoot this molecule with light, and then we end up with a molecule that an electron that shoots off, and then we end up with one electron between here, and then this electron can go on either of these atoms, and the one that it goes on right here will be a radical, and the other section will be a carbocation. And it's important to note that only the carbocation is actually can actually be seen and detected by this instrument. So what we're going to see is that when the production of the radical cation occurs by the electron impact ionization, the subsequent fragmentation is we're going to detect a lot more of the more substituted carbocation because the electron's going to go generally in the way that will produce the less substituted radical and more substituted carbocation, the more stable carbocation. So when we're doing mass spectra again, the purpose of the mass spectra, one of the big purposes is to determine the molecular weight of the organic compound. And so when we do that, we want to be able to try to take a guess at what the molecular formula is. And we should be aware that for a saturated hydrocarbon, the number of carbons is 2 times, or the number of hydrogens is 2 times the number of carbons plus 2. For example, if we have propane, in propane, each carbon has 2 hydrogens. But then there are 2 hydrogens on the end. So these are the 2N right here. 2N is these hydrogens right here. And then the ones on the end are the plus 2. So this one and this one here are the plus 2. 2N plus 2. And this is true for any saturated hydrocarbon that doesn't have a ring. And what we can do is analyze the mass and try to guess at how many hydrogens there should be. And that can help us, and given the functional groups that we know, this can help us determine what the molecular formula is. So for example here, if we have C5H12, this 12 is 2 times 5 plus 2. That's equals 12. But if we have a double bond now, essentially notice we had 2 hydrogens here, and we had 3 here. So now in the double bond, we essentially lose 1 hydrogen from each carbon. So for every double bond, we have 2 less hydrogens. So we say that a double bond is 1 degree of unsaturation. And a DOU means we have 2 less hydrogens. Okay. Likewise, a triple bond will constitute 2 DOUs. You'll have 4 less hydrogens than the saturated alkane. Here, like in the case of C5H12 versus C5H8, that has 4 less hydrogens. Also, if we have a ring of any kind, a ring will be 1 DOU because the plus 2 on the 2N plus 2 involves the 2 hydrogens at the end, like these. But if it's in a ring, there's no hydrogens there. The carbon's bonded to the carbon on the other side. So let's say we had C4H6 and we're trying to figure out what could be the structure here. Or we have what we think are these structures and we're trying to see if that's consistent with our expected molecular formula from the mass spectrum. We always say if this were saturated, you always look to the saturated. It would be C4H2 times 4 plus 2. So that would be C4H10. And so what would be consistent is a structure that would be consistent would be one that has 2 degrees of unsaturation, which could mean 2 double bonds here with 4 carbons, or it could mean 1 triple bond, and the triple bond could be in the middle between the second and third carbon, or at the end between the first and second. We could have 2 rings, so this has 4 carbons and 2 rings. We could have 1 ring and 1 double bond, because each of those is 1 degree of unsaturation. So this, when you start to get the mass from the mass spec, and you are thinking about functional groups from looking at an IR, let's say the IR tells you have a double bond, carbon-carbon double bond, then you can assume that at least one of those degrees of unsaturation that we see here is coming from the double bond, and you can narrow down your choices like we did here. These are all the choices that have 2 degrees of unsaturation are consistent with C4H6. When you're analyzing a mass spectrum, the first thing you want to look at is the so-called molecular parent ion. This will give you the molecular mass of the compound. So if the molecular ion is odd mass, that generally indicates that there's a nitrogen atom. The reason because nitrogen makes 3 bonds, whereas carbon and oxygen only make 2. So an odd mass peak indicates an odd number of nitrogen atoms. An even mass peak either means the absence of nitrogen or an even number of nitrogen. So, for example, if we have 1 nitrogen atom here, this molecule has a molecular mass of 73. And if we wanted to, so let's say we look at our structure and want to see, is this consistent? Well, this would take 5 carbons, 4 carbons rather. And let's say we know from the IR we have a nitrogen. And so then we're going to have NH2 here as well. Now we just have to figure out how many other hydrogens we might have to add up to 73. So we've got 4 carbons here, and those weigh 48. We've got a nitrogen, 1 nitrogen, and that weighs 14. And then we've got 2 hydrogens so far on the nitrogen, that weighs 2. So let's see what we have left. We have 6 and 8, 4, and 1 more, 6, 64. And so how much mass we have left? Well, the total mass is 73. Let's say we got that from the mass spectrum. And these atoms that we've assumed are in the molecule now would have a mass of 64. So that means we have 9 more, which may indicate that we have 9 more hydrogens here. And then that would add up to 9, and then that would add up to, at this point, 73. And so this is the kind of calculation you do to figure out what would be the number of atoms given a certain molecular mass. And if the molecular mass is odd, that's a dead giveaway that there's a nitrogen atom. That would usually be confirmed pretty easily from an IR spectrum as well. When we look at the our molecular ion peak, often there's going to be a little peak off to the right, the molecular ion plus 1 peak. This is due to the presence of carbon-13. About 1% of all carbon atoms are carbon-13. So here in methyl, we only have 1 carbon atom. So if most of these are going to be carbon-12. So the carbon is carbon-12. Carbon-12. So if we have 1 carbon, which weighs 12, and 4 hydrogens, which weigh 4, that's a total mass of 16. And so we see our mass over charge here, our mass at 16 is the highest. But we've also got a little one here at 17. And that one is due to carbon-13. You can see it's about 1% of the total height of the other one. So basically, this ratio is 99 of the carbons are carbon-12 to 1 being carbon-13. So you get a 99 to 1 ratio. But every time you have an additional carbon in the molecule, you have an additional 1% chance of any of these carbons here being carbon-13. So if you have 10 carbons, that ratio, like let's say we had 10 carbons, that ratio would go down to 90 to 10, and so forth. Every time you add an additional carbon, you add an additional chance to have a carbon-13. And so the ratio of the molecular ion and the molecular ion plus 1 can give you an indication of how many carbon atoms there are in the molecule. Next, you should analyze the M plus 2 peak. So you should see if there's an M plus 2 peaks, So here you can see there's a molecular ion, it's the biggest one here. And then there's a molecular ion plus 2. The molecular ion's at 112, the molecular ion plus 2 is at 114. And this ratio of this peak is 3 to 1. When you have an M plus 2 peak with a ratio 3 for the molecular ion, 1 for the M plus 2, that is an indication of the presence of a chlorine atom, which its natural abundance is 3 to 1 for chlorine 35 versus chlorine 37. So that's one thing you want to check for early as well. If you have an M plus 2 that is almost the same height, it's slightly less, 51 to 49%, that's an indication of a bromine atom. Finally, another thing to talk about here is just hydrocarbon fragments. And so you're going to see an abundance of hydrocarbon fragments in most organic molecules. And these hydrocarbon fragments will come from the loss of smaller pieces of the hydrocarbon. So for example, if we have the molecular ion of pentane here, this pentane can split in the end. Let's say this is the electron that's removed, right? So now it's only one electron. If this splits in this fashion where the electron goes with the methyl, then that's going to leave this carbon with a positive formal charge. And you're going to get this detected peak, which has all the mass of the initial one, molecular ion, but it's missing 15. So M minus 15 is indicating the loss of a methyl, and you should be able to also draw the remaining fragment, which is the butyl, as long as you've got an idea of the structure. Likewise, a similar thing could happen here if instead the electron is knocked off on the second bond. Again, you can have breakage here. In this case, the positive formal charge would be here. That's what's going on here. It's a breakage here. And we get these. And this is M minus 29. So you want to be looking for M minus 15, loss of methyl. M minus 29, loss of ethyl. M minus 43, loss of propyl. And M minus 57, which is the loss of butyl. Remember that the mass spectrum only detects the positively formal charged fragments. So this would have mass 15, mass 29. So that would be the complement here. And a lot of times you'll see both complements too. Like if you're looking at a mass spectrum of this, you're going to see a significant number of both chunks. You're going to see a significant peak at this part here weighs 29, but you're also going to see a specific peak here at M minus 29, which is in fact 43 here. And 43 and 29 add up to the total mass there. So here's an example of that same fragmentation pattern in pentane. And again, what you see here is you see the molecular ion. The molecular ion here is at 72. And M minus 15 here, this, you should be looking, what's 15 less? Okay, this is 57. That is 15 less. And so we see a pretty significant M minus 15 peak. Now the complement to that is the M minus 57 peak. The total mass is 52. So 15 plus 57 equals 72. Not 52, 72. Right, so here's the complement fragment as well. So what you can see is that it's not fragmenting very significantly at the first bond. It's more fragmenting in the middle. This is the M minus 29 peak. So this one actually is at mass 43. And this 29 peak is the complement at mass 29. It's M minus 43. And so that's this kind of breakage here, as I talked about these two. These two here are complementary to each other, and then these two here are complementary to each other. Right here, they in total add up to the 72. And so here we're getting a more even mixture of both, and we're getting significantly more breakage here in the middle than the other one. So look for those fragments of hydrocarbons, M minus 15, M minus 29 in particular, in most mass spectra. Finally, if you have fragmentation that can produce two different ions. So here, if we have a fragmentation right here, all right, where is the radical going to go? Well, the radical is more likely to go in the position that's going to produce the more stable tertiary carbocation. And so this electron likely goes here, leaving this as positive, and the electron is stuck right here. But this produces a more stable tertiary carbocation. So where a tertiary or resonantly stable carbocation might be made, you will get particularly large peaks shown in the mass spectrum. And so you definitely want to look at those large peaks and see, are those, the loss of a certain thing. Here, this is M minus 23, loss of propyl. Uh, Now, you may wonder, why don't I see a lot of propyl? Like, propyl would be the one where we have the positive here, CH2, CH2, CH3. How come we don't see a lot of that? Well, it's because the alternative, this one, is much more thermodynamically stable and will be produced much more than its complement here, this one. You're not going to see a lot of the propyl. You're not going to see a lot of this. You're going to see a whole lot more of this. And that will mean that peak is quite large. Instead of getting, like here, you saw kind of an even distribution of both complements. In this case, you're going to have a heavy distribution towards the more stable carbocation in the mass spectral peaks. Finally, when it comes to alcohols give very distinctive type of results. First of all, you should look for M minus 18 in water, and that is in alcohols. That's a loss of water, so that will indicate to you an elimination. In addition, alcohols tend to undergo what's known as alpha cleavage, where the alpha and the beta carbon break bonds. One of those electrons, so here we have the oxygen being the place where the electron was removed. So it's got an unpaired electron here. That unpaired electron goes into the double bond here, pi bond of this one, and then we have a breakage of the bond. And what you're going to notice here is, well, we have resonance here, which makes these particularly stable. And so you're going to see a lot of these in the spectra. And so this can be a good indication of alpha cleavage, that there's a lot of these here, or that these peaks are particularly large. Also, you get the loss here. This fragment is even in number. You end up seeing even numbered fragments as well. And again, the elimination of water here can also produce for you an even numbered peak, M minus 18 here, which would give you an even numbered value. Amines can undergo a similar alpha cleavage here, just the same as the alcohol essentially, except there's only one lone pair on the nitrogen instead of two, but you get the exact same result. Finally, carbonyls undergo this McLafferty rearrangement. And that's something to keep close eye on. Again, McLafferty rearrangement, dead giveaway here is going to be this even mass fragments that are produced in these. And when you have a carbonyl, you're going to want to look for these two larger fragments that are produced, particularly this one, which is resonantly stabilized. So here, though, you have to have at least 1, 2, 3, 4 carbons, because this is going to involve the fourth carbon away and its hydrogen. So you'll have a breakage between the alpha and beta carbage, kind of like in an alpha cleavage. However, that's not going to be the whole story. One electron will go into one of these, the alpha atom here. One will go into creation of a pi bond. On the gamma carbon, the third carbon away, it's going to break its bond with hydrogen, leaving one electron to create this pi bond. So these two electrons here will create this pi bond right here. And finally, the hydrogen moves over and attaches itself to the oxygen. And we still have this lone electron here. And so we have an allylic electron, essentially. And so this allows us to do a resonance here, where the electrons are delocalized, and we can draw the pi bond here. And the remaining electron here is a lone electron on the oxygen. And so that's something to look out for when you suspect a carbonyl in a larger molecule. So in summary, when we're analyzing spectra, we want to look at the mass spectra to determine the molar mass of the compound and the fragmentation pattern to figure out what atoms were bonded to what other atoms. As we go into NMR spectroscopy next week, we'll have another powerful tool to use along with mass spectra and the fragmentation patterns, to determine what atoms were bonded to what other atoms. But for the mass spectra, look for the alkyl fragments. First, start by looking at the molecular ion, right? The M plus 1. And then look for the M plus 2, looking particularly for chlorine and bromine. And then look for these alkyl fragments. So these are the alkyl fragments. Up to 47 right here. And then if you have an alcohol, you may get M minus 18. That will really give you a good indication that you have an alcohol. And then if you have a carbonyl, you may have a McLafferty rearrangement, which you can see very clearly because you will get a significant even numbered peak after that, and it will be significant due to that resonance stabilization of the carbocation. So that is it for spectroscopy as well. This has been a complete review of Chem 212 in approximately 5 hours rather than an entire semester. If you want to dig in a little further, you can look on my YouTube for my complete Chem 212 videos if you're feeling weak on a particular topic. But I hope that for those of you, you're coming into this class and it's been a while since you've seen organic. Hopefully this was useful to you to get the big ideas across. And we will continue here and continue to refer back to these Chem 212 materials as we move forward. And that will be it for this week's lectures. I look forward to seeing you next week as we discuss nuclear magnetic resonance.